Well, my dear participants, I am going to talk about law of large numbers. It states that, now first I would like to read these things from my document and then I will come on law of large numbers. It states that as n tends to infinity, this implies x bar converges to mu converges to the population mean, sample mean converges to the population mean with probability in the sense of probability. Thus, for large sample size, sample mean x bar converges to population mean as n tends to infinity. Height of American woman. In this example, we estimate heights of American woman from normal 64.5 inches plus minus 2.5. Try to see the behavior of sample mean which converges to the population mean. Basically, this example, height of American woman, have been discussed in the book of Introduction to the Practice of Statistics by Moore, D.F., McCabe and Craig. They are the three professors in the University of Purdue. So, I have taken this example from there and I have tried to explain the concept discussed in that book using R. So, here x bar S apply 1 is to 1000 and function we have defined function mean R norm n 64 point this and 2.5. So, what it will do? It will implement this function, that is, it will generate random sample of size 1 and it will compute its mean and SD, of course, and then it will repeat this problem how many times? 10,000 times. And then we can plot x bar and it is in the limit of 0 to 1000, and ebb line we will add a line which will be at mean. So, at mean and LWD is line width is 2 and its color is blue. So, C as x, note that we have used a new function sapply whose first argument is a vector or listed data and second argument is the expression which calls the first argument repeatedly. For example, in the above situation, sapply repeatedly calculates mean of random sample of sizes 1 is to 10,000. The graphic output are reported in the above figure. This is the graphic output. So, if we go on the R commands, see here, this is the chunk of R commands. Here we have generated how many samples? 10,000 sample means which are taken from a population of American heights with mean 64.5 and SD 2.5. So, it is taking a random sample of size is determined by here 1 is to 10,000, 1 then 2 then up to 10,000. So, it will generate x bar. See, it has generated 10,000 sample means, and then we can make a histogram of those. Here plot x bar, it is a plot, not histogram. It is a plot x bar. It is a kind of time series plot in which on x axis the time is the sequence and x bar is on the y axis. So, here it is plot x bar, and then we are adding a line 64.55 LWD and color is blue. So when we run this chunk, we will get a plot like this. See, here, as n increases, this whole converges to mean 64.5. And see, just after 4,000, we are, even after 2,000, it is converging. So it is converging towards mean, and this is the law of large numbers. Now we can see whether, just I am going on the PDF document, see whether it works for SD or not. That means as n tends to infinity, this implies S converges to sigma in probability. So what we have to do is that we are using S apply, and we are using it at the, we are using this S apply on SD. This is the function SD. So, and after getting 10,000 SDs, we are making the plot of that, and see here S is on the computed SDs are shown on y-axis, and here this is the sequence of observations. So up to 10,000. So as it goes near to 10,000, it converges to the SD, and that is 2.5. So that means this law of large number holds for SD also, and from the above graph it is evident that law of large numbers works well for SD also. Now we are going to talk about a very important concept of central limit theorem. Central limit theorem provides foundation of the sampling theoretic approach, CLT, and that is, its definition is very simple. If xi follows normal with mean mu and variance sigma square for I is equal to 1 to n, this implies x bar converges in law to normal distribution with mean mu and variance sigma square by 1. This is known as central limit theorem. Note that in CLT, even if parent population is not known, the sampling distribution can be approximated by a normal distribution. Here you see the parent population is not specified. Here it is just a population with mean mu and variance sigma square, and here, but we are specifying the distribution, and that is, so in the sampling distribution of x bar, we are specifying the distribution and its mean and SD also. So that way it is a very excellent result, and this result was first discovered by de Moivre. De Moivre was a French, and he was Protestant by his creed. So actually he was punished and he was sentenced 2 years jail term. So, and after that he left France and went to London, and with the expectation that he will be given some benefit, but he could not get any benefit there. So actually he developed first central limit theorem, that is known as de Moivre's theorem, and actually de Moivre's contribution is very significant in the sense that the CLT was later generalized by, because he has worked for central limit theorem when parent population is binomial or Bernoulli. But later in 2009 and 2010, Laplace gave the central limit theorem, and in 2010 Gauss gave it, but it is contributed to Gauss. So, but 70 years earlier to 2009, to 1919, 1909, prior to 1909, 70 years back, um, he developed this central limit theorem, and he identified the central limit theorem of de Moivre. But unfortunately, he could not publish that. So, you know what he did? He published it in the form of a pamphlet, and that was discovered after, when these central limit theorem given by Laplace and Gauss were developed. After that, it was discovered, and people came to know that Gaussian distribution was developed by the de Moivre 70 years prior. So, here we are going to talk about central limit theorem when parent is standard exponential. Suppose that parent population is a standard exponential and sample size is 10 taken to see the sampling behavior of the sample mean. Because this standard exponential is a kind of right skewed distribution, so we want to see what is the effect if parent population is right skewed on the distribution of sample mean. So, here we know a well known result, fx is equal to, this is the density of exponential distribution with expectation is equal to 1 by lambda and variance of x is equal to 1 by lambda square. Hence, SD is 1 by lambda. Thus, for standard exponential, lambda is equal to 1. So, its mean is 1, SD is 1, and expectation of x bar is n. SD is 1 by square root of n. CLT, using CLT, one can approximate the sampling distribution of sample mean by a normal distribution, normal with mean 1 and SD with 1 by square root of 10 if we take n is equal to 10. Note that exact distribution is of sample mean is gamma distribution with shape is equal to 10, rate is equal to 10. Keeping in view these facts, we use the following R commands. Simulate 1000 random samples of size 10 from exponential distribution. So, x bar 10, replicate 1000 and expression is equal to mean REXP. So, it will generate 10 observations from a standard exponential and it will compute its mean, and 1000 times this process will be done. So, the mean of those 1000 observations, 1000 means is 1.00, which is very close to 1, the exact value, and SD is actually nothing but it is 1 by square root of 10. So, they are very close, and we can make its histogram and we can compare normal distribution and exact curve. See, histogram x10 prob is equal to true, y lim is 1.4, curve d norm x 1 1, this is the normal distribution with 1, mean 1 and SD 1 by square root of n, that is 10, add is equal to true. So, it will add this normal distribution on the histogram, and then curve d gamma is the exact distribution and shape is equal to 10, rate is equal to 10, add is equal to true, LTY is equal to 2. So, this is the dashed line. So, this is the exact line and this is the central, this is because of central limit theorem. So, normal approximation is this one and exact distribution is this one. So, we see because of being right skewed distribution, it is not working in an excellent manner. Legend top right, and legend is equal to C normal approximation and then exact, and LTY line type is equal to 1, 2. 1 is the solid line and 2 is the dashed line. So we have generated legend also. Figure 1.2, this is the figure. Comparison of exact and approximate sampling distributions of sample mean n is equal to 10 from standard exponential. Note that approximation is not excellent as n tends to 10, as n equal to 10 only. What happens when n is equal to 100? We expect that it will improve the approximation. The whole story can be seen in the following R commands. See here, now simulate 1000 sample means of size 100 from the exponential distribution with rate is equal to 1. So here, instead of having size 10, now we are keeping the size 100, and then so every time it generates a sample of size 100 and then it computes its mean, and this process is repeated 1000 times. So x bar, mean of x bar is 1 and SD of x bar is this 0.10. And see, now we have given the command of making histogram. See, histogram here, normal approximation and exact, they are very close. Whereas in the earlier case, when the sample size was 10, so they are differing to a great extent. Whereas when sample size is 100, they are very close. So this is the central limit theorem. As n tends to infinity, it converges to the normal distribution. Now we can run these commands here. See, I have already talked about SD. So here it works for SD. As n tends to infinity, SD approaches to 2.5. So these are the commands and these are the output. Now central limit theorem, I have already talked about central limit theorem. These are the expressions I have already talked. Now to generate a random sample, simulate 1000 random sample means from of size 10. See this is x bar 10. Mean of x bar, it should be around 1, and SD of x bar should be 1 by square root of 10. SQRT of 1 by 10. So this is the exact value 0.316 and approximate value 0.3078, which we have obtained on the basis of simulation. Now we can make histogram and we can add a normal curve on it, and then so these are the commands, and when we run this is the graph. Histogram. This is the normal approximation and this is the exact result. So here the difference between the two is somewhat larger as compared to what happens when our sample size is 100 instead of 10. If we increase the sample size, see what happens. See, x bar, mean of x bar, SD of x bar. So here SD is nothing but 1 by, it is SQRT 1 by 100. So it is 0.1, and 0.103 we have got on the basis of simulation. So they are very close, they are very close. And here we have made a histogram of x bar 100, prob is equal to true, y lim is equal to 0.4, curve d norm x, mean is 1, SD is 1 by square root of 100, and add is equal to 2 to add on histogram. Then we are adding exact curve d gamma, shape is equal to 100, rate is equal to 100, add is equal to true, and LTY is equal to 2. And then we are putting a legend on the top right, legend on the top right position here, legend on top right, legend normal approximation exact, and LTY is equal to 2. So here when we run these commands, see, this is the position of top right and these are the legends, and see here when we are having sample size of 100, these approximation improves. So this is because of center limit effect. As n tends to infinity, x bar converges to normal. So it is normal. Now see what happens when we can go for sampling distribution with binomial with parameter 0.5, and if we select binomial with parameter 0.1, then if we simulate observations from binomial population with parameter 0.1, p is equal to 0.1, then what could be the excellence, what could be the approximation of center limit theorem. So these things I will discuss in my next lecture.